I gave you these 5 groups, Z2, Z6, U6, U7, and U9, and asked you, among these 5, which are isomorphic to which? We were able to very quickly figure out why every group is isomorphic to itself, and so we put a check mark down the diagonal of this chart. Every group is isomorphic to itself just by this magic function called the identity function. Send every element to its very self, and that will be not only a one-to-one and onto function on the elements, it will also have the homomorphism property and therefore be an isomorphism. So isomorphism is a reflexive relation among groups. Every group is related to itself by isomorphism. Also, isomorphism is symmetric. As soon as we established, for example, that Z6 was isomorphic to U7 via this function, for example, 3 to the x mod 7, we also get automatically that U7 is isomorphic to Z6 just by taking the inverse of this function. And the inverse of the 3 to the x mod 7 function is log base 3 of x mod 6. Right? So given any isomorphism from G to H, its inverse function is an isomorphism from H back to G. Right? So isomorphism is also a symmetric relation. Transitivity also holds for isomorphism. If G is isomorphic to H and H is isomorphic to K, then G will be isomorphic to K. And the isomorphism is taken to just be the composition of these two functions. Right? If f is a function that takes me from G to H in an isomorphic Xerox machine, and if I then run this Xerox copy through another Xerox machine to get K, right, then the copy I get at the end is still a copy of the thing I had at the beginning, and the copy machine is just the composition of G with f. So isomorphism is also a transitive relation. If G is isomorphic to H and H is isomorphic to K, then G is isomorphic to K. So what does this, by the way, all tell me about isomorphism? These 3 things combined together. What do we call that? Yeah, it's an equivalence relation. Isomorphism is an equivalence relation. And really, there's a real sense in which, you know how I've been saying how abstract algebra is abstract? We only care about the properties of groups, and we don't care about the specifics and the superficial differences between groups. That's because what abstract algebraists and group theorists study, we don't study groups. We study isomorphism classes of groups. If we only care about the structures themselves, and we don't care about the names of the elements or the names of the operations, we are studying equivalence classes up to isomorphism of groups. Ultimately, if 2 groups are isomorphic to one another, we want to blind ourselves to the differences between them and just focus on their essential properties and those that distinguish them from other groups. So that is what we study, groups up to isomorphism, or equivalence classes of groups. And so from an equivalence class perspective, there is no difference between Z6 and U7. They are equivalent to one another. They belong to the same isomorphism class. Okay, so let's fill in a couple of these boxes that we were having a little bit of trouble wrapping our heads around. First of all, Z2 and U6. Why was this one an interesting question? How come we couldn't rule this one out right away? Both Z2 and U6 are groups of what order? They're groups of order 2. And so a logical question is, well, just because their orders are the same, is that a guarantee that they are isomorphic groups? Not a guarantee. Not yet. But that our whole last act of this course is going to be about answering questions like that. If I know the order of 2 groups, can I conclude that they are isomorphic? Or might there be more than one possible structure that we can make with a same number of elements? So it's still a valid question for us. 2 look different groups of order 2. Are they in fact different, or are they the same? So what did you find out about Z2 and U6? If we want to make an isomorphism from Z2 to U6, what's the first thing that I absolutely must do?
Identity to identity.
Let's send identity to identity. We know for sure every isomorphism has to do that. So what therefore has to go to what here?
0 has to go to 1.
0's got to go to 1. 0 is the identity of the additive group Z mod 2, and 1 is the identity of the multiplicative group U6. So if we're making an isomorphism, if it has any chance of being isomorphic, 0 has to go to 1. All right, what else? Well, if this is going to be a one-to-one and onto function, which an isomorphism must be, that means that what else has to happen in this function? 1 has to go to 5. There is no other possibility for a one-to-one and onto function. So if there is an isomorphism between these 2 groups, this is what it must look like. So now the only question is, how do I know this is an isomorphism? It's one-to-one and it's onto, but why is it necessarily true, if I call this function phi, why is it always true that phi of x combined with y is the same as phi of x combined with phi of y, where combined is the operation of each of these respective groups? What's the operation in Z mod 2? addition modulo 2. So I'll put a little 2 under there just to cover my bases. What's the operation in U6? Multiplication mod 6. So a little 6 under there just to remind myself. Okay, so why is this true? Did anybody come up with a formula for this function that could be used to demonstrate the truth of this statement? I think I saw it in at least one group walking around. Jared?
5 to the x mod 6.
5 to the x mod 6. That one will do it. Because if we unpack what this equation would be telling me for this function, on the one hand, if I take x plus y first, and then I apply this function to it, I'm going to get 5 to the x plus y mod 6. I'm going to put my mod 6 out here at the end. On the other hand, if I did phi of x first, followed by phi of y, and then I combine them together with the operation in my group, I would get that. And what do you say about this equality? Is this always true for any x and y? It is. It's true for any x and y that are integers. They're equal on the nose, and therefore, of course, they'll be equal as residue classes mod 6. So, yeah, these groups are isomorphic, and that's an example of an isomorphism between these two groups. So coming back to our chart for a second, let's fill that one in. Green check mark. And again, we're using here f of x equals 5 to the x mod 6. So Z2 is indeed isomorphic to U6. So what about U6 to Z2?
Yeah.
It's a yes. And we could find what function do you think is going to be the isomorphism there?
The inverse of that.
The inverse of that.
Log base 5.
Log base 5 of x taken mod. So this one's going to be mod 2 because the range of my function here is z mod 2. Right, so that will be the inverse function for this. So if one of them is an isomorphism, so is its inverse function. So before we go to this last example, is there a common thread that we're seeing here? Like, why are all these exponential functions doing the tough work for us? Why are they uniquely well suited to this task? One of the reasons that makes exponential functions uniquely well suited to these isomorphisms is that for sure when I raise something to the 0 power, the result is going to be 1. Right? And 0 is the identity in my additive group, 1 is the identity in my multiplicative group. So these exponential functions are always sending identity to identity. What else? Why exponential functions are uniquely well suited to this is that they transform addition into multiplication. Right? And in fact, when I teach algebra, this is usually how I explain exponential functions to students, and they're learning them for the first time. The job of an exponential function is to turn addition of its inputs into multiplication of its outputs. It intertwines the operations in arithmetic of addition and multiplication of real numbers or integers or whatever you happen to be working with. That is the job of exponential functions. And so this product rule, this homomorphism property, is always satisfied for any exponential function that we can choose. Right? So that means that any time I'm taking a group whose operation is addition and comparing it to a group whose operation is multiplication, I should try an exponential function to do this, right? Because this thing always happens. This homomorphism property will always be satisfied. So you might look at Z6 and U9, which is, again, an additive group and a multiplicative group, and say, well, why don't we just try to write down an exponential function that can do this? And I'm just going to pick one at random out of a hat. And I'm picking this very specifically because I want to make sure to get to Valencia's question. But if I pick out of a hat, sorry, you can't read that very well. Let me write it in a better color.
Isn't that U7? U9?
You're right. U9 has different elements. Thank you. Good catch. That would have screwed me up in a second. Let's head that off at the pass. Right. We want U9 here. And so I want, what are the elements of U9?
1, 2, 4, 5, 7, 8.
Thank you. 1, 2, 4, 5, 7, 8. Great. Fix that. And so now let me pick the function phi of x equals, I don't know, let's pick 8 to the x mod 9. There's an exponential function, right? And so because this is an exponential function, this thing will satisfy my product rule, right? This is going to satisfy phi of x plus y, which is 8 to the x plus y mod 9, is equal to phi of x times phi of y, because that's 8 to the x times 8 to the y. Done mod 9. Right? So it satisfies that homomorphism property. Is this thing going to be an isomorphism between my groups? let's take a look and see whether or not this 8 to the x function is in fact an isomorphism. So 8 to the power 0 is 1. 8 to the power 1, 8. 8 to the power 2, 16, right? And no, 64. And 64 mod 9 is, uh-oh. I'm going to stop right now because why?
It is not 1 to 1.
This function is not 1 to 1. Exactly. Yeah, we should have picked 7, right? We should have picked something else, right? 8 clearly doesn't work. Even though it meets the product rule property, the homomorphism property, it's not a 1 to 1, and therefore also not an onto, because these are finite groups. It's not a 1 to 1 and onto function. So this is not going to give me my isomorphism. So as Valancius says, let's pick 7 instead and see if 7 gives us a better time. Let's see what happens. So 7 to the first power is 7. 7 squared is 49, and 49 is 4 mod 9. Then if I multiply that 4 by another 7, 4 times 7 is 28, and 28 is 1 mod 9. 7 didn't work either. Oh, U7. Well, we already knew Z6 was isomorphic to U7. We did that one on Monday. But yeah, choosing 7 to the x as my supposed isomorphism doesn't work either. So what's going on here during the activity? So what's going on here? So Z6 is, what do we know about Z6? The properties of Z6 as a group. What is it? Z6 is cyclic. What are the generators of Z6? 1's a generator, and 5's a generator. How do I know that there are only 2 generators for Z6? Phi of 6. The Euler phi function of 6 is equal to 2. Right, so there's 2 generators for this cyclic group. 5, 6 equals 2. Whoops, I used the curly phi when we talk about Euler. 5, 6 is 2 generators. Okay. And so if it's true that these 2 groups are isomorphic, what must be true about U9? It's got to be cyclic, right? If 2 groups are in fact the same, they both have to be cyclic. Right? And so that means that U9 had better have 2 generators also. So can we find, and this is the trick now, right? Can I find a generator for U9?
Yes.
What's an example of a generator for U9?
2.
Okay, and how would we have known that? That's not an easy answer, really. How did you find that out?
We
Just test it, yeah. You can test that this actually generates U9 just by looking at the powers of 2. 2 to the first power is 2. 2 to the second power is 4. 2 to the third power is 8. Multiply that by 2 again, and you get 16, which is 7. Multiply that by 2 again, you get 14, which is 5. Multiply that by 2 again, and you get 10, which is 1, and then we've got them all. Right? So 2 generates this whole group. And because 2 generates this group, what also for sure generates this group? The inverse of 2. And what is the inverse of 2 mod 9? Because 2 times 5 is 1, mod 9. And now that I've found 2 generators, we can stop, right? Because there can't be any more than 2 generators because it's a cyclic group of order 6. So now that I know that both of these groups are cyclic and I know what their generators are, how should I make an isomorphism between these 2 groups? What must that isomorphism? Make the generators go to the generators. A generator on one side is going to be an element of order 6. A generator on the other side is going to be an element of order 6. And my isomorphism has to connect the 2 of those things, right? Because the order of any element has to agree with the order of its image under an isomorphism. The order of G has to equal the order of phi of G. And so an element of order 6 has to go to an element of order 6. So I could send 1 to 2, or I could send 1 to 5. So I have 2 choices for how to make an isomorphism between these 2 groups. What would be an example of a function which would send 1 to 2 and be a homomorphism? Just following our earlier pattern. Just try 2 to the x, mod 9. That's going to send 1 to 2. And because it sends a generator to a generator, we can show that it becomes 1 to 1 and onto for that reason. Right? Because all 6 of the powers of 1 are going to be different. And because my function is 1 to 1, therefore, all 6 of the images will be different. Because different goes to different under a 1 to 1 function. And so this 5x equals 2 to the x mod 9 will be an isomorphism between these 2 groups. What would be one more example of an isomorphism between these groups? What's the only other? 5 to the x mod 9. That'll do it. Right. So there's two isomorphisms between these two groups. Because there are two automorphisms of the group Z6. Because, and I was telling this group that as I was walking around, and I just want to get this onto everybody's notes at least. The other thing that the U groups do, so the groups UN, they're valuable not just because they tell us about multiplication of integers, but they're also valuable because they're isomorphic to the automorphism groups of Zn. So all of the isomorphisms from Zn to itself can be put in a one-to-one correspondence with the invertible numbers mod n. So there are two invertible numbers mod 6, right? 1 and 5. This is my U6 group. And because there's two elements in U6, there are two ways in which a cyclic group of order 6 can be isomorphic to itself. And in this example, these two functions account for those two ways. So when we fill out our table, we can put a check mark here. We can put a check mark here. And then to close, can I say whether U7 is isomorphic to U9? Without doing too much new work.
You
I
put
know.
the check mark in the wrong column.
I did, didn't I?
Yeah.
I put the check mark in the wrong column. They moved that. Meant to put it here. There we go. So can I say whether U7 is isomorphic to U9? I can say it, but is it true? So we can do this. We just have to get Z6 to bridge the gap. U7 is isomorphic to Z6 by one of these functions. It's already in my table, right? U7 is isomorphic to Z6 by this function, log base 3 of x mod 6. And then Z6 is isomorphic to U9 via the thing we had on the other slide. And so we can conclude, yes, U7 is isomorphic to U9. Something you might want to do is come up with a formula for that isomorphism by taking the composition of the two isomorphisms. This 2 to the x mod 9, for example, is one of the ones we could use here. That completes the table.